So we're going to talk about what's inside SEF, or SUSE, Enterprise Storage, SEF. A little bit of tuning on object storage, and then thinking ahead, some considerations for massive scale with object storage. So what's inside? Just a little bit of an overview about the SUSE vision for enterprise storage. SUSE Enterprise Storage is based off of SEF. It is, your data anyway, anywhere, anytime. It's truly unified, distributed object store, and based on SEF, and resilient and self-healing. Just this week, I don't know if you knew this, but the SES Foundation was formed on Monday, so that's pretty cool. It supersedes the SEF Advisory Board that was created clear back in 2015, and it is directed underneath the Linux Foundation. SUSE is a founding member, and we have many of our employees. Lars Morawski-Brie, our distinguished engineer, sits on the Foundation Governing Board. The technical leadership team is filled with a lot of our SUSE engineers that manage different parts of the upstream code, from the SEF Manager dashboard to the monitoring framework, the deep sea deployment tool, a lot of things that SUSE has put a lot of investment in upstream. These aren't the only contributors to the upstream, but we have many other engineers that also contribute. These are just our engineers that are on the leadership team there on the SUSE, or on the SEF Advisory Board. Just to go a little bit deeper, if you don't know anything about SEF, SEF strictly is written on top of a common object store called Rados. And below that you have storage nodes with disk that gives you the whole entire infrastructure. You have monitor nodes that manage and monitor the infrastructure, the laying down of that data on your disk. Welcome, guys. I'm glad you could make it. I like the green hair. On top of that, we have different types of access. Of course, SEF gives you that unified access to block, file, and object. So let's dig into, right now, a little bit of the SEF tuning. So I've been doing a lot of performance tuning and testing for SEF with many different customers. Not just all object, in many different access types as well. So if you have questions about other access types besides object storage, we can kind of go into those after I talk here. But some of the results, we'll go through the setup here. The setup that we used in this really small scenario, which actually performed quite well, surprisingly, given the hardware that we had. We were using Dell 740 XDs for the storage. We were only doing 16 OSDs on it. We were pairing that with 2 SSDs, so we're doing a hybrid setup with the SSDs for journaling. So we had a 1:8 ratio there. 128 gigabytes of RAM on each one of those nodes, which really for those ones was actually a little bit overkill. And then we had 10 gig network cards on there, and those were bonded together. And then the client nodes that were connecting to it, they also had 10 gig as well. So we had 10 gig all the way around. So when we did our testing, we got really great performance. Monitoring nodes were all tie-in systems. They had about 128 gigabytes of RAM, which really is a bit of overkill as well. But I mean, they were fine for this particular test. It of course didn't use up all that RAM. So some of the results that we got, we load tested it with Workload Wisdom. Are you familiar with Workload Wisdom? Nope. Okay. This actually does a great test when it comes to objects. You can actually have it load up. It does a cloud-based load testing. So it actually loads up many different clients. You can actually choose how many clients you want to load up. And with the clients that you choose to load up on, it will actually prepare a bunch of data into the cluster. So there's a preparatory step that it goes through, and it loads all the data into the cluster so that it can do a bunch of reads and different writes, a bunch of tests that goes through. And then you basically start a test. You can tell it hey, I want to do 60% write, 40% read, or you can do a 90-10, or you can mix and match however you want. In this particular case, we were connecting directly to object storage. You could use it for block and file as well, but Workload Wisdom does a great job of actually tracking the metrics there. So in this case, we were loading up 15K actions per second, and we were doing about 8,500K IOPS on this particular cluster. So given the cluster, it had a 10 gigabyte backplane. That's actually not bad. We had about 5 storage nodes. If we had more, it probably would have performed a little bit better. We probably could have gotten a little bit higher IOPS on it. We were doing probably around 4 gigabytes per second. So we were actually saturating that 10 gigabit link pretty well. We might be able to get just a little bit more out of it if we had more nodes, a little bit more throughput. So failure doesn't stop us. What's interesting about the results during the testing with Workload Wisdom is that as the system was going through the test, this first box here, that's when a whole node was pulled out of the cluster, an entire storage node. I mean, it barely caused a blip in your IOPS during the test. Everything continued to run and go, but then when the system came back up and running into the cluster, you saw this, it started going down in performance, and then it went back up again. Once it was fully restored, the system actually performed a little bit better. The IOPS went up just slightly, which was interesting to see. Just a little bit more on some of the results here. The commands per second, so what you're seeing at the top right is the IOPS during one of the other tests that we did. We went through a slew of different performance tests based on different tunables that we applied to the system, enabling and disabling the Spectre meltdown patches and stuff within the Linux kernel and various other things like that. Total throughput, 32 million kilobits per second there, which translates to around 4 gigabyte a second. So tuning for the object storage, and this is really some of the important stuff to kind of understand when you tune for massive scale. Object storage, to consider some of the use cases here, you can use it for massive scale architecture. It's extensible as far as the metadata is concerned. So unlike other architectures, when you're dealing with block and file, you don't have this extensible metadata infrastructure. So you can build in your own tagging and mapping with your objects. And you can search it with Elasticstack if you want to apply that to your infrastructure. And there's really no restrictions in geography when it comes to an object storage infrastructure. And that goes with Ceph as well. We can architect this across the globe. It's also used for active data, streaming, media, HPC. We've seen it in a lot of these areas at SUSE. So consider high IOPS and throughput when you're considering object storage. Some of the components that I want to go through here is the system as a whole. Each hardware vendor has their own HPC guidelines on how you disable specific things within the system so that you get lower latency. So follow that guide for sure on every one of your systems. And then I'll go through some disk and network Rados gateway tuning here. Network tuning, there's a lot of things that you need to apply to your sysctl on the storage nodes. Making sure that, specifically right here, your mem max and your defaults, those should all be much higher. So your buffer pool is much higher when that data gets streamed. One thing that we noticed when we enabled this was our backlog was actually reduced, and our streaming of the data actually flowed through much more freely than it did before with the defaults that the Linux kernel came with. So tuning your network is going to be very important. Some other things to keep in mind are the low latency and the fast open. Those are very important, especially for the Linux kernel. Enabling the low latency on the networking stack is a very important parameter to enter in there. If you don't have that, then the streaming of data that comes through gets blocked up just slightly. And you can notice that through many of the tests that we've done. Disk tuning. So this is an interesting one on the disk tuning side. Enabling block MQ for the disk. So instead of using the default scheduler within the kernel that your distribution comes with SUSE, you're going to be using the CFQ scheduler by default. You could use deadline and some other things if you wanted to. However, for the block device on Ceph, you definitely want to enable block MQ. MQ will give it to multi-queue capabilities, so take advantage of the multi-cores that are in that system. When you go ahead and you purchase a storage node for Ceph, you want to make sure that you purchase something that has lots of cores when it comes to your CPU cores in that system. And then you can take advantage of the multi-queue capabilities. So basically what you're doing, in essence, is you're queuing that and utilizing all the cores at once instead of actually using the CFQ scheduler and using only single or double cores in a system, and you're taking advantage of the hardware in a much greater way. This actually speeds performance up quite a bit. And this is not only for object storage, but also use this for block and for file as well. Use it all the way around in Ceph. Another thing that we've done here, no PTI, no spec, no Spectre V2. That's turning off the Spectre meltdown stuff. Most of the time, your Ceph cluster is going to be completely isolated anyways. Nothing else is going to touch that. You're going to be connecting directly to monitor nodes or some other gateway for the services. So disabling that is not going to be some heartache. So this is actually some recommendations that we've put into some of our documentation so that you get a little bit more performance boost in your clusters today. And we've seen where it's actually degraded cluster performance by about 20% in some cases, which can suck if you really want a performance cluster. Rados gateway tuning. So take a look at a few things. The thread pool size and the usage max user shards. I didn't play around with this one too much, but I did notice that going in between the value of 2 and 4, 4 is kind of a sweet spot. 2 didn't really do a whole lot, but going beyond 4 really caused the performance to degrade with the Rados gateway. The number of handles, the Rados handles, 1024 is kind of a sweet spot that I hit. Anything more than 1024 really caused the performance to go down. And this could have been because of the systems that I was using, possibly. But even the thread pool size, there are some documents out there that will tell you to keep the thread pool size much lower. But if you have a lot of RAM, you can bump that up to a much higher value. I put it at 4,000. I tried higher values. It didn't help increase the performance, which could have been due to our 10 gigabyte network. If we may have had a network on the back end that was a lot larger, our thread pool size, if I would have bumped it up, may have caused performance to increase. But we couldn't tell because we were saturating our network anyways. So, so that could be a tunable that you bump up in your cluster if you're running a 25 gig backend or high. Things to consider for massive scale. So when you're scaling up to 50 petabytes of storage, 100 petabytes of storage, consider a leaf spine network. Leaf spine networks give you the best for east-west traffic. You really don't want to do a north-south traffic infrastructure for your SEF environment. And today you're doing a lot of cloud-native infrastructure workloads, which really aren't the greatest running on top of a north-south network infrastructure. It's best to use an east-west because it gets you the best bandwidth and the highest bandwidth possible, and it's highly scalable and fault tolerant going forward. Some of the network layout that you really need to consider is really, if you're buying new hardware, don't consider the 10 gig anymore. Start considering 25 gig. I mean, the price is just, it's low enough now that it just doesn't make sense to do 10 gig anymore. Make sure you're setting your MTU to 9,000 on all of your nodes and all ports. With SUSE Enterprise Storage, we typically have a management network that'll tie into your hardware, and then we have our SEF public and SEF cluster networks. So we'll have 2 pairs of bonds for our 25 gig backend on there, and then usually in mode 1 for LICP. Some things to consider for massive scale out architecture on the storage nodes. You might want to consider a one-size-fits-all, because if you're buying hundreds of these, you don't want to have to, buy one at this size, buy another at this size. It just makes sense to do one system that's exactly the same for all hundreds of nodes that you're buying. And these are some basic calculations to consider for how to calculate your RAM, things to consider for the CPU speed. Monitor nodes, make sure you've got the fastest CPUs available. You don't need a lot of RAM because all those monitors are doing is doing a lot of computation. If you're doing a one-size-fits-all, it doesn't matter in this scenario, but smaller cluster sizes, you might want to consider these objectives here. Any questions?